A crystal is a material where the atoms, molecules, or ions are packed in a repeating three-dimensional array. We see crystals throughout nature, not just in things like gemstones, but in many of the materials around us. What we don't often see at all, though, are crystals that not only repeat in space, but also repeat in time. A time crystal. But a scientific team has just built one that lasts for 10 million times longer than the previous record. A time crystal that hints at unlocking a world of new possibilities in our understanding and control of complex systems. But what does that breakthrough actually mean, and how does it work, and what might it mean for our future? My PhD is in optical nanophysics, and I really wanted to dive into the details to really understand what was actually happening here. So prepare yourselves, we're going full frontal physics. Let's start by taking a look at time crystals in general, then try and understand exactly what happened in this experimental breakthrough. Although common, crystals are fascinating materials to study because they have emergent properties from how the atoms within are arranged. The simplest type of crystal is a repeating cubic structure. Strangely enough though, there's only one element that forms this type of crystal, polonium-210, a product of the radioactive decay of uranium-238. If the atomic spacing between atoms in a crystal repeats the same way in all directions, the word for that is isotropic. But if it has some structure and some direction, and other repeating structures in other directions, we call this anisotropic, and it can lead to some really interesting effects. For example, sapphires conduct heat at different speeds along different axes due to the difference in the atomic spacing in different directions. This can be a really useful property in things like high-powered LEDs or lasers or other high-powered applications, so you can draw heat away from your equipment, away from the substrate, and manage the thermal performance of the device. But what happens if a crystal structure isn't just repeating in the three spatial dimensions, but also repeats in the fourth dimension of time? What if a crystal axis had time as one of its dimensions?
Here is an ordinary square. Whoa, slow down, egghead.
This idea was the foundation of Nobel Prize-winning physicist Frank Wilczek's deceptively sophisticated concept, a time crystal. For Wilzcek, to qualify as a true time crystal, the material would have to repeat a behavior as a function of time, maybe changing its structure or its energy levels, and importantly, it would need to continue this repeating pattern forever, not just temporarily like ringing down of a tuning fork after it's struck. This constraint disqualifies things like chemical clock reactions, which are fascinating but eventually consume their reactants and stop oscillating. Instead, in Wilczek's version of the time crystal, the behavior would need to repeat when the system was in equilibrium, without needing further energy in or refueling. In quantum mechanics, this is called the lowest energy state, or the ground state. The challenge here was finding a system with no energy left to give up, but was still constantly repeating and changing, which sounds kind of impossible. It also sounds suspiciously like a perpetual motion device. In fact, Wilczek felt similar, stating in his seminal paper in 2012, a system with spontaneous breaking of time translation symmetry in its ground state must have some sort of motion in its ground state, and therefore be perilously close to fitting the definition of a perpetual motion machine. In this paper, Wilczek considered a superconducting ring, where charge carriers, which let's just say electrons for our purposes, were free to move. The lack of resistance in a perfect superconducting material would mean that the electrons could travel around the ring forever. If these charge carriers were arranged with a regular pattern, then this sounds like a perfect candidate for a time crystal. So let's talk about this idea for a minute, because it tells us where this concept of time crystals actually stops working. Superconducting rings are a surprisingly old concept, with their properties demonstrated nearly 100 years ago. In 1932, in a lab in Leiden, Gerrit Flim induced a current in a lead ring cooled by liquid helium. Flim then flew to London to present a Royal Institution lecture, where he showed that 200 amps of current was still flowing in the ring. As all moving electric fields also produce an associated magnetic field, Flim further demonstrated the current's presence inside the ring by placing a compass next to it. The needle of the compass deflected towards the ring. This is interesting and proves that the current is still there, but it also shows us a problem in why these superconducting rings cannot be perpetual motion devices and ultimately cannot be true time crystals. If the charge carriers affect their environment, even something something as small as deflecting the needle of a compass, these interactions are leaking energy from the system, which even if it takes a very long time to happen, will eventually cause the motion of the current in the ring to stop. Slightly frustratingly, Wilczek waves away solving this minor but really quite major problem as an exercise for the reader, stating that simple variations can ameliorate this issue, such as the use of multipoles in place of single charge carriers, embedded the system in a cavity, or simply arranging that the motion is slow. Unfortunately for Wilczek, actually solving this issue turned out to be anything but simple. The debate over the possibility of a Wilczek-style time crystal continued until Haruki Watanabe and Masaki Oshikawa looked deeper into the mathematics behind Wilczek's idea, ultimately concluding in their no-go theorem that time crystals in equilibrium are prohibited in the universe for reasons that seem perfectly okay, like you can't have perpetual motion devices in our universe. Superconducting rings could not continue forever, no matter what modifications were made to them, so the original idea of the time crystal was dead. Or was it? Fortunately, a small modification remained that evaded the no-go theorem, but raised its own kind of questions. To compensate for the inevitable losses to the surrounding environment, energy or order needs to be supplied into the time crystal on an ongoing basis. Having to top up the systems means that this is not in equilibrium, which was part of the appeal of time crystals in the first place. As Watanabe and Oshikawa state, oscillations of non-equilibrium quantum states are well known and should not be called time crystals without further justification, which in a research paper is basically as close as you get to scientific smack talk. Something was needed to bring back the magic of time crystals and justify their maybe overly glorious name. The first experimental signs that the time crystal could still be something special come from University of Maryland in 2016. By suspending ytterbium in an ion trap, Christopher Monroe showed that the ion levels could be induced to oscillate at frequencies lower than the driving frequency supplied by a laser, a phenomenon called subharmonics. These are arguably pretty unintuitive, and the only example I could actually find of something that was a little bit more intuitive is a niche singing technique where a lower note is produced by combining a bunch of higher notes. Within the material, the ions essentially picked up their own frequency, even though the frequency that they were being bombarded with was different and higher. This was ultimately a breakthrough, but it wasn't really that satisfying. Deriving an oscillating energy output from a system where the energy input is also oscillating, that was confusing to get my head around, feels kind of like cheating and doesn't feel like the time crystal is actually doing the majority of the work. In 2022, just a decade after the original idea of the time crystal was first introduced, a breakthrough in this approach was finally made in Hamburg, Germany. By cooling rubidium atoms to near absolute zero, a continuous time crystal was finally demonstrated inside an optical cavity. The laser that was providing the energy to this system had constant power applied to it, but the atomic density of the crystal started to oscillate. So in this instance, although we had constant energy being put into the system, we had a material change in that system that was oscillating as a function of time. That sounds pretty cool on its surface. There was only one downside with this crystal. It lasted only for about 10 milliseconds. So again, it feels a little bit underwhelming. And for those of you that are shouting at the screen at the moment and saying, how about just a quartz crystal being used in a watch? Isn't that just a time crystal? Well, yes, it is a crystal and we use it to tell time, so you're right, but it's actually being constantly driven to expand and shrink at certain frequency using something called the piezoelectric effect. And that's a problem because that falls into our first example's trap of using an input energy that is oscillating to ultimately produce an output of that system that is also oscillating. It's just not that exciting. We want something that is totally independent of its environment shaking around. Luckily, a few hundred miles away, Alex Greilich's research team at Dortmund University realized that a new approach was needed. An approach that would ultimately produce a time crystal that lasts for 10 million times longer than the previous approach. As this breakthrough is I think as much about how they did it and what they did as the actual outcome that they got out of it. And because obviously I'm an experimental physicist and this is the fun bit for me, I want to talk about exactly what the experimental approach was in detail. So that is your warning. Full frontal physics, like I said, incoming, feel free to look away. And we are about to cover a bunch of pretty hard topics, but trust me, I think you can handle it. I wanted to run through this to see exactly how they achieved their results. Let's start with a regular gallium arsenide crystal. Viewed along one axis, it has a regular recurring pattern that we would expect from a crystal. Greilich's simulation work suggested that the complex behavior of time crystals wouldn't be possible with this lattice structure alone. The symmetry had to be broken because Greilich's goal was to create an oscillation of the time crystal through interactions of the nuclear spin and electron spin within the crystal. And don't worry, I'm going to explain what that means. To do this, he introduced indium atoms in place of some of the gallium atoms, approximately 3% of them in total, and that's a process called doping. Greilich then placed this crystal in a cryostat at about 6 degrees Kelvin, or about minus 267 degrees Celsius. These indium atoms created distortions in the lattice that rippled outwards. This means that the electrons now experience different fields based on how close they were to their local indium atom. To make time crystals actually work in our universe, we said that we need to input energy into that system, but we wanted that energy to be nice and continuous, not oscillating. To provide energy in and to compensate for the losses to the surroundings, Greilich used a pump laser, which just means a laser directed into a system with the explicit purpose of providing energy into that system. The wavelength of the laser used to do this was 785 nanometers, which used to always cause me anxiety in the lab when we used to work with lasers of that type, because they're basically invisible to the human eye, but they are oftentimes powerful enough to instantly blind you if you're unlucky enough to be in the wrong place at the wrong time. So there's always this fun game that happens within the laser lab of how do you work with the basically invisible near instant death laser. Greilich used this laser not just to give energy to the system, but also to give it order. He used circularly polarized light, which is where the beam polarization appears to rotate as it moves through space. The polarization is the photon spin state, and it means that all photons are delivering the same energy in the same order into the system. As that pumped laser beam hits the crystal, the photons impart their spin to the electrons in the crystal, which start to align the electron spins throughout the crystal. This essentially serves to mostly uniformly raise electrons into a higher energy state. We said already that electron movement or electric field movement can cause magnetic fields. As the electrons start to have their spin aligned by the pump beam, the magnetic field effects of these electrons begin transferring this spin to the nucleons through something called flip-flop processes, causing a polarization of the nuclear spins nearby. However, for a reason I couldn't actually find in the paper, the magnetic field arising from those nuclear spins doesn't actually align perfectly parallel with that of the electron spins. So that constant input laser energy is causing the electron spins to align, which is exerting some force on the nuclear spins, causing them to partially align, which is then pushing back on those same electron spins. This causes them to precess, essentially rotate around their axis like a gyroscope at an angle. The precession of those electron spins as they start to oscillate around their axes changes how much they are pushing on those nuclear spins, which changes how much those nuclear spins are pushing on the electron spins, which creates this essentially complex oscillating dance back and forward, or the very first inclinations that we're moving to a time crystal. If this all sounds pretty chaotic, you would be absolutely correct. This was literal chaos theory in action. The starting conditions of the system dramatically impact the eventual end conditions of the system, which is actually a bad thing in time crystals because you want a regular oscillation coming out of your system. In order to achieve this, Greilich had to damp the chaotic emergent behavior coming out of the system. He did this by applying an additional magnetic field to the system tilted at 10 degrees to provide a small bias to the system's motion. That magnetic field applied at a tilt of 10 degrees moved the system out of this chaotic regime and into a self-oscillating system. This was the theory anyway. Obviously, this is all happening inside the crystal and we can't see any of it. How do we actually measure and prove that a time crystal is in front of us and vibrating and doing its thing? This is harder actually than it might already sound, and it already sounds pretty hard. Another thing that makes studying time crystals difficult is that any large input of energy can accidentally destroy the delicate oscillations inside. We call this melting in the context of a time crystal. So our goal is to study the system, but without disturbing it too much that it stops being a time crystal. The answer to how we do this, obviously, is
more lasers! You can take more time to answer the question if you like. More lasers!
A second beam, called a probe beam because it probes the system to see what's happening, is added into the experimental setup. This laser was a longer wavelength of 850 nanometers, which was linearly polarized, so all of the polarization states of the photons were either moving in the Y direction or in the X direction, rather than a circularly polarized corkscrewing their way through space. This second laser is made to pass through the crystal, and what happens to the laser on the other side of the crystal will tell us whether this is a true time crystal or not. In order to understand how that part of the experimental approach works, we need to introduce a final, kind of hard concept needed for this experiment. We can think of linearly polarized light as the combination of left and right circularly polarized light, aligned so that it essentially cancels that circularly polarized corkscrew effect so that it is continuously polarized in just a single direction. We saw already that inside a material, circularly polarized light interacts with the electrons, which in turn create their own magnetic field. Depending on which way the circularly polarized light is spinning, it will impart, and as a result experience, different effects from those electron spins. If it's spinning the same way as the pump laser is, it slips through the crystal pretty easily. If it's spinning the opposite way, it's essentially working against the pump laser, trying to flip the electron spins in the other direction, which makes its journey harder. The end result is that these two different circularly polarized beams travel at different speeds through the material. And what this means is that when they emerge from the crystal, one is slightly ahead of the other. These are still, remember, recombining though to produce linearly polarized light. That linearly polarized light will now just be tilted at a small angle relative to the input angle. So that means that two things should be happening if this is a true time crystal. One, that the angle of the light as it emerges from the crystal should be slightly tilted relative to what it is when it was put into the crystal. And two, because of the continuous oscillation between the electron spin and the nuclear spin and their kind of continual interference, this tilt should be slowly varying in nature, but only to a very, very, very small margin. The tricky bit, as if all of the previous steps were not tricky, is the experimental job to detect really accurately how much shift in polarization angle there really is. There is, luckily, a very interesting and clever way of doing this. You can split that beam of light into its linearly polarized components using a polarizing beam splitter. In theory, if you aligned this perfectly with the input polarization initially, you could then measure how much light was in the original polarization and how much was tilted into a new angle, and watch as that amount of light slowly oscillated due to the inner workings of the time crystal. The major problem though is this signal is a very minor oscillation of the tilting signal as a whole. You probably see some level of signal coming from this system, but the interesting time crystal oscillation piece of it would probably be lost in the noise of the system as a whole, coming from things like the laser or the environment, the imperfect nature of the mirrors that you were using, or the beam splitter, basically everything. So your challenge is how to remove all the noise associated with everything so you can just see the signal that you are interested in. And we do this using math with light. By introducing a half wave plate into the beam, which rotates the polarization of light, we can rotate it so that rather than a big signal in one beam and a very small signal in the other beam, we have equal signals on both. We can then put each of these two laser beams onto two photodiodes and subtract the output of one from the output of the other. This means that if we get some laser noise, it will be present in both branches if it comes from something like the laser or the environment. The difference should be your time crystal oscillations. So what do we actually see? This. Take a second to look at how strange this actually is. It's a repeating pattern, absolutely, but it's far from maybe a sinusoidal wave, but it's not a million miles away. It's also incredibly slow in its nature. It has a period of 6.9 seconds. As an optical physicist, I'm used to dealing with optical oscillators with 80 million oscillations per second. So one oscillation every 6.9 seconds is slow. So what is exactly setting the timing of this oscillation isn't overtly apparent. Asking how long it takes to flip an electron spin isn't necessarily a straightforward question, but it's definitely a negligible part of this time period. I'm amazed at how long-term and emergent this behavior can be from basically instantaneous changes to electron spins. So that's really interesting. Zooming out, it's pretty clear that the time crystal shows no sign of ceasing its oscillation during the 40-minute experimental run. So although the result is, hey, this thing lasted for 10 million times longer than the last one, actually, it isn't really showing any signs of stopping. In the paper, they say, as we observed no indication of any oscillation decay for 40 minutes, we can safely conclude that the time crystal lifetime is at least a few hours, potentially even longer, which feels to me like the ultimate hand-wavy answer. It lasts for somewhere between 40 minutes and the lifetime of the universe, maybe longer. As with any good experiment, the creation of the first stable continuous time crystal raises many questions. I'm very curious why it has the characteristic M shape. It might just be how the math is mathing to create that M shape, and maybe something about a DC offset for the subtraction step that I mentioned earlier, but without seeing the exact experimental setup, I can't really say. In the paper, it acknowledges the details of the observed variations are not yet fully understood, which is basically, hey, we did a thing, but exactly the nature of it, we're still trying to understand what is specifically happening and why it's happening that way. Scientific papers often feature quite dry writing, as it were, such as, we leave, however, the detailed theoretical modeling of the dependence of the continuous time crystal periodicity on different parameters for future investigations. And again, this just says this is very early science, we've done a thing, we're trying to work out exactly how it works, because we aren't quite sure yet. That says to me that there is still much to learn about these time crystals. It's clear that this research isn't the beginning of the end for the time crystal research, but it is the end of the beginning. As for applications and why this thing is actually potentially useful, Gerrit is interested in the great sensitivity it has in changes to magnetic fields, as well as potentially a timing standard. But honestly, it feels like it is way too early to look at time crystals and ask how they will be used, because we just don't really understand them sufficiently yet. It's only been a decade since the original idea was conceived, which is kind of exceptionally fast when it comes to physics, especially when the idea is how do I make a crystal that repeats its behavior in the fourth dimension. But that brings us to the end. This is a cool breakthrough, mostly cool because its unbelievable complexity of its experimental setup and just the depth of understanding of how to build this system and how to measure it and how to control it is really interesting and absolutely at the forefront of things that we understand. I hope you enjoyed this video. If you did, leave a like down below. If you have an idea as to what a time crystal could be used for that would be practical in the real world, let me know in the comments section. And thank you again for watching. I'll see you next time. Goodbye.